Yeah, they're interpreting evolution backwards. The whales came onto the land and evolved further inland. And when they come to shallower depths, they grow more accustomed to the shallow and then the land and then the trees and so on. I mean, they come to the land. They're claiming they lose their legs. They mutate toward Sirenian like animals. The connection here is Perucetus and the stellar sea cow. These guys actually sunbathe. Here's a whale skeleton. It has 5 fingers, a little proto hip. This isn't something that existed and then lost it. It hasn't had it yet. This is a seed hip. And Perucetus, the largest whale-like Sirenian animal that we found that rivals the blue whale, links them together. And ultimately, the more they come onto the land, they're going to adapt little fin-like legs. The fluke of the tail splits essentially, and the hips actually connect to muscles here, and it gives them a type of leg. So the tail's receding and splitting into legs, and that hip is getting bigger. And Odobenocetops, which is the walrus-faced whale, links those guys together. And look, this evolutionary chart here just evolves in a circle. There's no progenitor. It's like this guy evolves. This is supposed to be out here, and all of these animals equal the same biomass as the largest animal. The laws of thermodynamics. Biomass is no different. It ties to energy and thermodynamics because it ties to the sun. Now here's Ambulocetus, the walking whale. Walking whale. It had to transition and walk somehow. It couldn't have just popped into existence from nowhere. And it's carnivoran-like. Here's Endohyus. It's carnivoran-like, but it's also got hooves. So it's related to artiodactyls because we know the whales are related to the artiodactyls, and it's related to carnivorans. That links the whales to the pinnipeds and to the cats and dogs, and to the bovine and the pig, and all these animals we are related to. And here's Pakicetus, same difference. It's got hooves, or it's a walking whale. It's linked to the carnivores, the artiodactyls, and the whales. Now this guy's related to the Sirenians. He's got 4 legs. So it's not that the 4-legged animal lost its legs and became a Sirenian, like a dugong or a manatee. It's that these animals are residuals of when they came onto the shore and evolved into various animals. And the same animals exist now that existed then. They just existed in a more primitive state then than they do now. So all the same animals exist and have existed, but they've existed in different various states. And thanks to insular dwarfism, whenever these animals get smaller, they trade a trait for another trait, and the trait advances. And just like with the EQ chart here, the smaller the animals get, the larger their brain gets. The Mysticeti is the largest animal on Earth, toothless whale, blue whale. It has a low EQ compared to the rest of the animals that are smaller than it is. And Hector's dolphin has a brain to weight EQ of 1.7%. Now the human has about 2% of the body weight. It's got 1.7. And the bottlenose dolphin, as smart as it is, only has 1.19% of its entire body mass. And it weighs 3.5 pounds. Now, this animal weighs 640 grams, which is about 1.4 pounds. These guys weigh 88 to 132 pounds, which is about as much as an average human woman. Now, I theorized that the Parvipelvia ichthyosaur, well, the ichthyosaur were ancient whales. And I know it sounds weird, but people are like, well, they can't be because they're skulls. I know they have reptilian skulls, or they have super amphibian skulls. They retain a lot of amphibious traits, but diverged independently of the Eggling lineage, which were amphibians and reptiles, and then birds, and then monotremes. So before the skull becomes synaptic, it's going to be diapsid. Technically, it's going to be metapsid or euryapsid, and then diapsid, which the skull has to be in a primitive state before it gets to an advanced state. So in early evolution, the skull was evolving, and so were other traits. And the whale lineage of the cetaceans and our lineage, which we're related to, retain those traits. So fish, or Sarcopterygian or Actinopterygian, one of the two, or lobe fin, ray fin, diverge. Now they say we're related to lobe fin fish, but there's ray fin and lobe fin, and we share a lot of DNA with the elephant fish. Now I'm not completely sure about that yet, but I do know some of these I got underlined that we are related to, for sure. And if they did the DNA, I guarantee it would be true. Now, the skull formation, like I mentioned, fish are anapsid skulls. So it's going to evolve toward euryapsid, diapsid skulls, making this some type of amphibious or super amphibian is what I call it. Friedrich von Huene actually hypothesized that it was an independent amphibian also back in 1937. But it retains the blubber. It's got 200 conical teeth like a dolphin, live birth, warm-blooded, same eco niche as the whale. That's the orca technically. And then it's got smooth skin. And there's actually several other traits that it actually could have retained, like a 4-chambered heart. I believe that the heart evolved 4 chambers real early in our evolution. But until we find a fossilized heart, which I believe we'll never find, then that's just a theory. But the theory is it was septated similar to a turtle's heart, which was 3 chambers and then 4, through the ichthyosaur lineage. And then they evolved toward basilosaurids and Durodon. But it's got a synapsid skull by now. Now, these guys are related to the Ambulocetus, Endohyus, Pakicetus, which are related to artiodactyls and carnivorans. Now, as basilosaurids are going to still evolve further because they're in the water, they still evolve. They mutate slower because they're larger animals. The more cancer-resistant, Peto's paradox. Peto's paradox makes evolution possible. The largest animals, they pass mutations slower because they're larger animals, metabolics, thermodynamics. So the mysticetes are going to come onto the scene. Blue whale, they have no echolocation, and they have no teeth, you might say. They have baleen, but that's not exactly the same thing as teeth, like the odontoceti, because these guys are going to evolve, and the brain is going to advance more, and it's going to get a little bit smaller, and you're going to have animals with echolocation, odontoceti. And then you have Sirenians, which are related to the whales through Perucetus, the stellar sea cow, because we just uncovered some stuff about the stellar sea cow's DNA that is whale-like. Proteins and such that they use, mutations in the same genes. And of course, those guys are related to the land animals, the hyrax and the elephant. No, these guys have tusk, which is ivory. These guys have tusk, which is ivory. Sperm whale, the tusk, which is ivory, teeth. The pinniped have ivory, and the hippopotamus have ivory. So you can link these guys through the ivory. Also, so you have Odobenocetops, the walrus-faced whale, and then he's related to the walrus, the pinniped. And since the sperm whale, or the odontoceti, the whales, are related to the artiodactyls, and they're related to the pinniped, that means they're related to the bovine, which is a family we are actually in. We're actually related to the bovine. We're in that family. And we're actually in the diprotodont family also. So there's Dasiomorphia, Didelomorphia, Diprotodont. That's the one we're in. Microbiotheria, Nothorictomorphia, also tuberculata, and Paramelomorphia. Of course, there's extinct ones, but they're all still related to these guys. Because once the DNA exists, it exists. One way or the other, it exists. These animals technically don't go extinct because they live on in the animals that exist now. So there's kind of like a fine line that needs to be worked out with the word extinct and what it actually really means. But yeah, we're related to the diprotodont. So I'm willing to bet that if we do DNA tests on all of these animals, we'll find out that we're actually closer related to the kangaroo, the wombat, and the koala than we are, let's say, a sugar glider or a possum. And I'm willing to bet that on anything. Now, I'm also willing to bet that the walrus, we're closer related to the walrus if we do DNA tests of all the pinnipeds, sea lions, elephant seals, and all the other seals and animals that are pinniped, that we're closer related to the walrus than we are the rest of them. And also, I'm willing to bet that we're closer related to the bovine than we are the other families of artiodactyl, with the exception of a pig. And the reason why is because of the gut. These guys are foregut fermenters, and pigs are hindgut fermenters like we are. So we're technically a cousin to the pig, but we're in this family because these guys are cousins to the pig. We're cousins to the pig, but we're closer in DNA because of our stomach, because of how our stomach is rigged, the DNA that controls our digestion. Because technically in early evolution, the first three things to evolve were the lungs, the stomach for digestion cavity, and the heart. And this was through the first stages of our as mycelium, because we were related to fungus. All life on Earth is a fungus. We evolved from fungus. Everything evolved from fungus. This is actually presynaptics. This is actually the early brain, because fungi, mycelium, it actually sends chemical signals. It communicates with each other. So this is early brain. And here's the sponges. These were digestive cavities essentially, but it's like siphoning to breathe through its skin, which is a heart function, and it's actually a breathing function, and it's a digestive function. So our heart, our lungs, our skin, sponge, pore bearer, flesh, and then there's coral, and this stuff is called brain coral for a reason. Mother Nature is evolving this stuff. These are going to become our organs, nerves, because these guys are related to the ctenophores, and the cnidarians, because they're floating nervous systems. That's why it looks like mushroom. That's a phylogenetic trait. And then, of course, sea squirts, tunicates are going to evolve. Now they actually end up going mobile, and the notochord is evolving. Now, typically this thing won't attach itself to the ground like a tadpole, but instead, in bad situations, it likely can't, and it remains mobile. But this is going to force an evolutionary response because, like neoteny, whenever it comes to an axolotl or salamanders, essentially, axolotls, they stay in their juvenile form as they grow up. And this is the juvenile form of a notochord, which is a chordate, which is a sea squirt. And through this evolution, that's when we're going to get agnathans evolving, the eel, essentially. Like hagfish and lamprey. They're agnatha. But eventually they're going to evolve toward fish and eel. And then they are going to diverge. The fish are going to evolve into salamanders, cecilians, and frogs. These are the amphibians. They diverge. So like we diverge, they diverge, the amphibians. That's what leads me to believe this has to do with an amphibian that evolved independently, because it was around about the same time as the amphibian, around the same time that the reptiles came onto the scene, but the amphibians evolved towards reptiles. So an amphibian evolved toward the ichthyosaur, which is reptilian-like. And these guys are anapsid. They evolved toward anapsids, which are amphibians. Now, the turtle is actually an anapsid too, but it's a reptile. And it's because of the way it lays its eggs like a reptile. And this implies to me that the birthing mechanism evolves before the skull does. And that's why this thing at least 300 million years ago is already laying or giving live birth. So it evolved from an ovoviviparous animal that evolved toward live birth. Whereas the fish that evolved toward these guys were still laying eggs, and they saved that trait and just advanced it. And then, of course, reptiles come onto the scene, like the turtle is a reptile, but then the skull evolves into a diapsid skull. So now instead of an anapsid reptile, you have a diapsid reptile. And of course, those diapsid reptiles are going to evolve towards synapsid reptiles, which are monotremes. Now, I know we classify them as mammals, but there's a lot of fine lines that can misconstrue this or confuse the data. It can confound the data if we look at that as a mammal instead of an artificial mammal. If we look at it like an artificial mammal, which is an endothermic reptile, then it makes more sense because it's technically in the reptilian lineage. It lays eggs, and its legs are positioned to the side of it. Whereas everything in this lineage, its legs are positioned underneath it, which technically means all sauropods are tetrapods, but not all tetrapods are sauropods. Now, tetra means four because so a tetrapod is 4 legs. A sauropod has 4 legs, but a tetrapod is technically positioned to the sides, whereas a sauropod's legs are positioned under it. So they both have 4, but the positioning is different. So that needs to be classified like that. It needs to be specified. And it's little specifics like that that kind of confound a lot of this information. And like the guy said, it's not the information, it's not the data that's wrong. It's people's interpretation of what they're leading us to believe that's what it is. That's what's wrong. They're leading us to believe the wrong thing about what the data is saying. Now look, temnospondyls evolved. They're the first amphibians to evolve. They're like the first animals on this planet, and they're already saying they evolved from a terrestrial ancestor. So where did that come from? You see what I mean? They're confounding the information. The animals that they're saying lost its legs has no origin. It's a grandfather's paradox in itself. It just pops into existence. And they even say that in a lot of evolution. They'll say, oh, well, this animal evolved at this time or that time. It just popped up. And they'll even say the words popped up in some cases. The mosasaur, this animal was huge. It was a large reptile. They're already saying it lost its legs to go into the life of the water. But this thing existed at least 200 million years ago, 150 to 200 million years ago. And these animals were the largest ones on Earth. The largest ones on Earth are going to make dwarf mutations toward the land, and they're going to evolve into various animals onto the land. But that giant animal itself isn't going to go anywhere. It's still going to remain in the water. And that's the reason why the theory is like, well, if we evolved with apes, then why they're still apes? It doesn't mean that they got to disappear. It just means that mutations were passed that were more accustomed to the land. So they have that backwards too. Now, even the plesiosaurs, as large as they are, they're another of the largest animals on Earth. It starts at the largest. You don't get more out of the way you put in. The laws of thermodynamics apply to evolution, no different than it applies to quantum mechanics, quantum physics, or biological or chemical evolution. It's all the same. It's energy. And they say they lost their legs and went back to the ocean too. In early Earth, when everything was seeded and evolved, it had a lot of energy. The animals grew to their maximum size, and then the energy stopped. It was consistent. It's not that it stopped necessarily, but the animals had reached their maximum size. And then over time, you have insular dwarfism, like I was saying, with the continents will break up, more shallow waters, so the animals get smaller over time. And the large animals evolve slowly and they pass dwarf mutations. Some evolve as different animals over time, and some stay as largely the same animal, but they just dwarf. But as they do this, they gain traits, and their brains get bigger. And just like a mouse has a large brain rate. It's got 1.4 EQ, the body to weight ratio, just like us. So, the smaller these animals get and the longer they've been on Earth, their brains are going to get larger. And we're actually one of the smallest apes. We average around the same weight as a chimp, but they're a lot denser than we are. But that density is traded for brain EQ. So we don't have to be as beastly anymore because we got a brain to be able to work things out. Now, the fastest metabolism, it's an Etruscan shrew. And look how small they are. They're one of the smallest animals. Mammals, per se. It has to eat 2 times its body weight a day. That's like me eating at least 300 pounds worth of food a day. And the hummingbird, its metabolism is 100 times faster than an elephant's. So it all ties to energy and biomass and thermodynamics, chemical energy.